Sorry, folks, those listening at home, I forgot to start this on time. We've been talking about this problem for a while. We went over the previous slide here, talked about that, and we had talked about this slide, and we're just about to do example 2, which this slide is covering. So I forgot to turn on Screencast-O-Matic until now. But anyway, now I try it again. And see, this is what gave it away. I can't click on black here because that would end Screencast-O-Matic. So I have to use the dark purple. And that's what gave it away that, whoa, I forgot to start Screencast-O-Matic. So here's your function. And they put it as a capital F of X. I don't know why. You can name it anything you want to. They cut F of X is a piecewise defined function that's defined this way. It's defined as X for all, aggravating, for all x's less than 1. It's defined to be 3 for all values 1 less than or equal to x less than or equal to 3. And it's defined to be x again for all x's greater than 3. Okay. Now, here is the function. Okay. This is the graph of that function. For all x's less than 1 is the identity function. 0, 0, negative 1, negative 1, negative 2, negative 2. Yeah, it's the identity function. 1 half, 1 half. 5/8, 5/8. 9/10, 9/10, 90, 900, 99 hundredths. Whatever, every value up to there, but not at 1. At 1, it jumps up and becomes 3. So, the question is the function, this f, as x approaches 1 from the left, where is it going? It's going toward a value of 1. But f at 1 is actually a value of 3, because this doesn't include 1, this does include 1. And its value there is 3. So the function as it approaches x from the left, it's approaching a value of 1, but the actual value of it is 3, as given here. So it's not left continuous. It is right continuous, because here, f of x, for x is greater than 1, okay, the value is 3, especially not much greater than 1. 2.5 and on down, Okay, that would be 3, so f of 1 is equal to 3. So that is left continuous, right continuous, because the function as x is approaching 1 from the right-hand side, the value is approaching 3, and of course, that's what the value is at x equals 1. Okay. Now, flip it over, and as x is approaching 3, from the left-hand side, the function value is 3 all along there. So sure enough, it's approaching 3, it's equal to 3. So therefore, it is left continuous at 3. At x greater than 3, on the right-hand side of 3, the function value as x is approaching 3 would be getting closer and closer to 3. Its value is 3 there, okay? So therefore, it is right continuous too. In other words, you can draw this curve without picking up your pen. You can't draw that curve without picking up your pen. So it's not, and you can't even get to 1 here. You have to draw your 1 up here. So it's right continuous there. Okay. The open circle means it doesn't ever reach that point there, but it does reach it right there. Now here's another question. Could that be a closed circuit there and a closed circuit there? A closed circle there? Why not?
Because it would mean that at that point it would be
two values. That would not be a function. We are dealing with functions here. That would be a relation, but not a function.
It would
Fail the vertical line test. So yeah, you can't have an open and a closed two closed circles at the same point. If they're not the same, you can here because they're the same point. So again, F, so again, f of 1 is the value 3 from this right here. X equal to 1, that value is 3. And so this one cannot be, as it's approaching 1, as the function is approaching x value of 1, the y value is approaching 1 as well. But it doesn't ever get there because when it gets to 1, it jumps up to 3. So the function value is not approaching what the actual value is. From the right, it is. The function value is 3, and it's approaching 3. And the function value is 3. Okay. From the left at 3, it's approaching 3. It is 3. So it's left continuous. But at 3, it's also right continuous, even though that's not defined at 3. It's approaching 3 as x gets close to 3 from the right, and its function value is 3 at 3. Okay? So it's a dumb-looking, made-up problem, but it is showing you what continuity is. Okay? Now, in reality, do you ever have things that really are sort of dumb-looking like that? Sure you do. Okay? If you had, and this is a dumb example even then, but it's reality, postal rates. Postal rates are not continuous functions. Anything less than an ounce is going to be, I don't even remember what it is now, 40 some or 60 some.
That sounds about right.
Yeah, 40 some, 40. Let's just say 48 cents, 42 cents, whatever it is. Anything less than an ounce. So the minute you get the instant that letter goes to 2 ounces, it jumps up and it's, I don't know, 72 cents or whatever it is. I don't know what it is. So yeah, that kind of stuff. But also in electronics, if you have a current coming into a diode, whether it's positive or negative, it's going to come out positive. Okay, that's what a diode does. It only directs current in one direction. So if you had, say, a dual diode system, which you do in your cars, when you're charging your battery, your generator there is doing alternating current. What a dual diode does is reverse the sign of it. Anytime it goes negative, it flips it back positive again, so you can charge your battery. So that way, you know, the function is wanting to do this, but it's really doing this kind of stuff. So you do have these breaks, and hopefully there's going to be something like that. Others.
That's cool. So you're saying, okay, I think I understand what you're saying. You're saying that instead of it making a full
sine wave,
it only stops. It makes bunny hops, and
that's how the physicists call them, bunny hops. Yeah, so I got that. Okay.
It eliminates the trope.
The negative. Yeah, exactly.
That's cool.
Because otherwise it'd be discharging the battery half the time and charging it the other half.
Right. So
and you don't want that to happen.
This only keeps it in the
and it applies to charge.
Yeah.
Now, another situation would be anytime that something would go positive, it gives you a +1 value. If it went negative, it would go you a -1 value. And you have things that do that too. That's how they do analog to digital. Because digital is always either 0 or 1, you know. So if you have something coming up in here, it's going to be a 0. In here, it's going to be a 1. So, you know, and computers, you know, digital systems only do 2 circuits. Yes, no, +1, 0, 1, whatever. Yet, and that's really what you do when you're converting anything from analog, say music or videos or anything else, to digital. That's exactly what you do in real life. And there's discontinuities there because you're only 0 or 1.
Can I ask a quick question while we're still on this? I think it would be beneficial for all of us. In the exercises table,
right.
This is figure number 14.
Okay.
I don't know if you have that. It's the graph that has a single line and that has a filled-in spot, and then the directly after that, it's a line that has 2 open circles.
Right.
Do you see that by chance?
Right. Yeah. Okay. Let's go over to that if you want to. which example is this? Is that
That's
example 1, actually? Referring to figure 14. So let's do that. Let me go and erase this one because I need the space.
And here, the whole reason why I'm even bringing this up is there's a segment of the graph that has the 2 open circles.
Right.
And then it has another open circle above and a closed circle below. So I just wanted to ask about that.
Right.
How that could exist. Well, not necessarily how it could exist because it still follows the vertical line test.
Right.
But just asking about it.
Yeah. Okay. We don't need that many. All right. Let's pick some points. At x equals 0, that looks to be 3.5, but it's not a node there, so just keep that in mind. 1, 2, 3. My spacing is not good, okay? But at x equals 1, it does have a value of 3. That we know for sure. It also has an open circle at 2. Okay.
Which makes sense.
And Rodney's here, talking about making sense.
Hey,
Okay.
perfect attendance.
Huh?
Perfect attendance.
Sorry.
Perfect attendance.
Yeah, okay. Well, except we added somebody.
Oh, yeah, okay.
Nathan Bryant. I know who he is, but I don't know if he hasn't shown up yet. But they just added him at the end of last week, so I don't know what's going on there. But anyway, we got another person. Okay. All right. This function does something like that. I'm not drawing as pretty as they got, but no. Okay, at x equals 3, we have the value of 1. Wait. X equals 3. 1. Okay. Whoa! Yeah, it is value of 1. But it also has an open circle.
2.5.
That's about right, I think. Okay. An open circle there. And what the function has done, it's gone from here to here.
Right, which makes sense.
Right. But also at 3, it has a value of 5. It doesn't have a value of 5, it has an open circle at 5. Okay? And then at x equals 5, you're down here, is that 1 or 1.5?
Yeah.
So let's say 1.5 at 5. And that's the closed circle, right? Yeah. And then it goes from there and does something else. Okay?
No.
And then there's a connection
the line
between.
connects from that one to that one, but there's another little.
Oh, no. I did it wrong there, didn't I?
Just erase the line going.
Oh.
Because
Yeah, I'm sorry.
You're right.
I don't know. I think I got to looking at the wrong figure. Okay, okay. No. Okay, I started looking at figure 15 for that last part, but I needed to be there. Okay, let me get this part erased.
And there's another closed
Yeah.
circle.
Open circle. Isn't there?
Or open, yeah.
Okay. It's an open circle
Or
at x
3.5.
equals x equals 5,
3.5.
around 3.5.
There we go.
Okay, right about there. Okay. And then
is
from
the
there, it goes somewhere like that.
Perfect. Yes.
Okay. Now I finally got it right. I'm sort of close anyway. All right. What are they asking here? This is page 82. This is 2.4 exercise, number 1, I think.
Yeah.
Referring to figure 14, state whether f is left or right continuous, or neither, at each point of discontinuity. Does f have any removable discontinuities? Okay, 2 questions there. Okay, so first let's identify our points of discontinuity. Everybody agree 1, 3, and 5. Okay, it's continuous left of 1, between 1 and 3, between 3 and 5, and past 5. Appears to be continuous there. Our points of discontinuity are those. So at each point at x equal 1, is it left or right continuous? How about it's left continuous at 1, not right continuous at 1. Okay? At x equals 3, left, right. Oops.
Would it be neither?
Neither. Okay? That's your neither. It says or neither. So this is neither.
That's because it only has that one.
Yeah. It's not left continuous because as x approaches 3 from the left-hand side, f, as it approaches that, f of 3 would appear to be, what, 2.5, when it's really 1. As it approaches 3 from the right-hand side, it looks like it should be going toward 5. It's really going to 1. So that's neither left or right continuous. Okay? Now, how about at 5?
The left continuous?
At 5, it would be left continuous
But not right.
and not right continuous. Very good. Because it's approaching 1.5 from the left, and it is 1.5. But it's approaching 3.5 from the right, but it's still 1.5 at 5. Okay. So you got that one right. Now, the second part of the question was, does F have any removable discontinuities? No. Okay. Because they're all jump discontinuity. It jumps there, and it jumps there. Okay? Now, if these two would have been somewhere, anywhere, that they had the same value, but both open circles, they wouldn't be left continuous or right continuous. But if you remove that, if you redefine F at 3 to be whatever that point was in common, then it would be a removable discontinuity. This is a jump discontinuity. This is a jump discontinuity. That's a jump discontinuity. No way you can remove any of those. Okay?
So, for instance, if that bottom closed point, if that was an open point, and let's say the open right above it was closed,
right?
Would the bottom, would that be a removable?
If this were open, you wouldn't see it.
Okay.
You only see it if it's the end of the line. Okay.
Got it.
Yeah. It means there's nothing there. So you don't just put an open circle here. The end of the line, you can put an open circle, or an end of a curve, or even in the middle of a curve, you can put an open circle. But you can't.
But you'll never just see a point.
An open circle without a curve on one end or the other, or both.
Got it. Okay.
Right. Good deal. Did that answer questions? Anything more on that? And frankly, folks, this is, I hate to say it this way, it's almost much ado about nothing, but it really does have meaning. The real calculus is coming later, but you have to understand this to know what we're going to be doing next. So, yeah.
I just know, well, at least for me, this was one of the things that kind of tripped me up
Yeah.
early on.
No, I'm glad you're asking. Yeah. You need to understand it, right? But to me, we're not really in calculus yet. This is all, it's sort of like getting the nomenclature, and understanding what terms mean before you can get there. Here's another discontinuity. We've had jump discontinuities, we've had removal discontinuity. Here's another one, an infinite discontinuity. Okay? I wanted to make sure I wasn't skipping something like I did on that first one, not realizing the figure represented a problem, an example. All right, here we have. This is a function. It looks like it goes to infinity this way. So coming in from infinity, it's coming in here, but when it approaches 2, it takes off and gets extraordinarily positive, infinitely positive, and never, ever can take on the value of 2. on the other side of 2, it's coming from positive infinity, coming down, and seems to be going that way. Now, you don't need to know this, and this isn't necessarily true, but here's one. I can't write on the screen with that. Here is one possible. Oops, as soon as I do this, it's going to reduce it. I'll hold off that for a moment. Okay, let's look at the V. Now, is that a jump discontinuity? They usually don't call it that. It's certainly not removable. Okay? It's an infinite discontinuity. Okay? Here's another example of one. This one coming in from negative infinity. Looks like it goes on forever that way, approaching 0 but never getting there, what it appears. Coming down, but when it approaches 2, it's going to negative infinity, never hitting 2, x equal 2, because it keeps getting infinitely larger, so you approach it from the left. From the right, it's coming from positive infinity. So boy, these are an infinity part, okay? These going like going to the same infinity. Infinity really isn't a number, but at least it's going in the same direction. But guess what? They'll never, ever meet. They won't touch. They can't. They can't equal 2. That's what dotted line means. It's a vertical asymptote. It cannot equal 2. But this one, can you get any further apart than that? Not really. Okay. So that is an infinite discontinuity. Now, this next one, and by the way, this is not left continuous at 2. It's not right continuous at 2 because there is no value at 2. You can't have one. Or that one. However, this one is left continuous at x approaching 2, but it's not right continuous at x approaching 2. Obviously, it's going on, but there's nothing you can do with that. It's going infinitely large. So it's an infinite discontinuity at x equal 2, not from the left, but from the right. But that is an infinite discontinuity. It can't be removed, and it's not counted a jump because it's not jumping to any particular value. So neither one of these. And remember, infinity is not a value. Negative infinity is not a value. That just says it keeps getting infinitely large or small, whichever you're talking about. This one has a value at x equal 2 as x approaches 2 from the left. It doesn't have a value for x equal 2 as x approaches 2 from the right. It doesn't have a value. It doesn't have a limit. It doesn't have an open circle. It doesn't have anything. That's an infinite discontinuity. Okay. Now, you don't need to know this, but just to give you an example. I don't know for sure this is this one, but it certainly could be f of x equal 1 over x minus 2 squared. That could be that function here. As x approaches 2 from the left, that's always positive. The denominator is always positive, never negative. But it's going to positive infinity from the left to positive infinity from the right. But it's not a removable discontinuity. It's not a jump discontinuity. It's an infinite discontinuity. Okay. The next one could be simply written as I'll just call it g of x. And this could be, doesn't have to be something like this 1 over x minus 2. Okay. The discontinuity is at x equal 2, and that can just be 1 over x minus 2. Okay. As x approaches 2 from the negative side, it is extremely large negative, like 1.9 minus 2 would be 0.1, 1 over 0.1, or 1 over negative 0.1 would be negative 10. And it went to 1.99. 1.99 minus 2 would be negative 0.001. 0.01. 1 over that would be 1 over 100. Negative 1 over 100. So from the right-hand side, that would be 2.1. Those would be positive numbers. Okay, now I can't come up with, well, I don't want to try to come up with what that function could be for the left. This would be a piecewise defined function. C would have to be a piecewise defined function. From the right, whatever it is, it has a value at x equal 2, but from the negative side, it has a value at x equal 2, but from the right, it has no, it's an infinite value. It gets uncontrollably large as x approaches 2 from the right. So that is also an infinite discontinuity at x equal 2, even though it has a value at x equal 2 from the right. Left, I keep saying it wrong. Okay. Does that make sense? Okay. Now, here is theorem 1, and they call this the basic. Now, I'm going to jump ahead. It's not ahead. This shows up in your book before that basic law does. This is one of those stupid ones. I'm sorry, I shouldn't say that. This is the graph of sine y is equal to the sine of 1 over x, okay? And this sort of drives me crazy, as if you hadn't guessed already, because this is not only you're trying to take a function of something that has no limit, okay? And you just can't do that at all, okay? This is not defined at x equal, as x is approaching 0. As x is approaching 7 or minus 3 or anything else, no sweat. But as x approaches 0, this argument is not defined. So how in the world could you even define what sine is? Because sine just keeps going through plus or minus 1. And as you get closer to 0, it's just getting faster and faster, and it just can't keep up. There is no value of this part at x equals 0, and then how can you have a value of a function of something that has no value? Okay, and that's why it does like this. That discontinuity at x equals 0 is not a jump discontinuity. There's no way you can remove it. Okay, it's not a fixed jump because they just keep going up and down in opposite directions. Faster and faster the closer you get, but you can't ever get there. So it's not a jump discontinuity. It's definitely not a removable discontinuity. It's not heading toward an infinity. This is, but the sign of that is not. Sine stays between plus or minus 1. So it's not an infinite discontinuity. It is none of the above, but it is a discontinuity. Okay? And they, for some reason, love this kind of an expression. I don't think that happens in nature ever. 1 over x doesn't happen in nature ever. So why do they make such a big deal about it? I don't know. Okay? But it's just showing you that is a it's calling it, some functions have more severe types of discontinuity, not a math word. Neither left nor right, neither jump nor removable, not infinite. It's none of the above, but it is a discontinuity. Okay, so let's go back to our basic laws for discontinuity. For continuity, not discontinuity. They're so focused on that, it's driving me nuts. Okay, so theorem 1 in this section. If f of x and g of x are both continuous functions at x equals c. Now what does that mean? No matter what f is doing at x equals c, it's continuous there. It could be coming in as a cusp, coming in at an angle, smooth, changing direction. It could be doing anything. Okay. F and g are both continuous at x equals c. Then the following functions are also continuous at x equals c. The sum of two continuous functions is a continuous function. The difference of two continuous functions is a continuous function. the product of a constant times a continuous function is also a continuous function for any constant k. Any constant k, even 0. Okay? Is infinity a constant? No, it's not a number. 4,743,852.5, that would be a k. But infinity is not a k. Okay? It has to be for any constant k. Any fixed finite number, k. No matter how large or how small. K times f of x is still a constant function, a continuous function, as long as f is continuous. The product of two continuous functions is always a continuous function, and the quotient of two continuous functions is always continuous as long as the f of c, this is that point c, as long as, g of c is not equal to 0. If g of c was equal to 0, that's not a continuous function anymore. That would be one that would do something like this at c, or this at c, or this at c, but it's definitely not continuous at c. But any time when t is anything other than 0, it is a continuous function. And it's the product of those, the quotient of those two values. Okay? Now, hopefully that looks pretty simple. Now in the old text, they didn't put the of x's in there. I don't know why. I'm glad they're putting them now. They do have a little proof here. It's worth taking a look at and reading through. But let's go on to the next theorem. Okay? Now, continuity of polynomial and rational functions. Y'all remember way back in pre-calculus. If you took it here, that was in Math 112, Chapter 2, polynomial functions. I believe it was the first 5 sections of Chapter 2. Capital P of x, that's how we usually denote a polynomial function. We put a capital letter here rather than a lowercase. And Q of x, capital Q of x, that they both be polynomials. Okay? Now, P of x, the saying here is any polynomial function is continuous everywhere on the real number line. Polynomial functions continuous everywhere. And not only continuous. They'll probably get to this later. Hopefully you remember this from pre-calculus algebra. Not only are they continuous, they are smooth. Things like I was describing before, points, cusps, things like that, not going to happen with a polynomial function. They're always going to be smooth and continuous everywhere on the real number line. Now, if they are, their sums are, their differences are, their quotients are still smooth and continuous. However, I meant to say product. I think I said quotient. Products are. Sums, difference, and products are. But the quotient, P of x divided by Q of x, is continuous on its domain. Now there's the weasel word. Continuous on its domain. What do I mean by that? Any x value that makes Q equal to 0 is not in the domain. So you have to exclude those values that make Q of x equal 0 because they're not even in the domain. That means all values of x equals c such that Q of c is not equal to 0. So everywhere else they're continuous, and everywhere else they are, I'm just going to say almost the same thing. But if you do have a value where Q of x equals 0, x equals some value c such that Q of x is equal to 0, then it's not continuous there. In fact, it's not even defined there. Okay. Now, they do a little bit of a proof on that one as well. And I'll let you take a look at that. Let's sort of give let me give you an example. Of course, when I do this, it's going to shrink. It's supposed to shrink. No, I hit the wrong key. Okay. Okay. Here's a function, f of x. It's equal to 3x to the fourth minus 2x cubed plus 8x. Okay? Number one, is that a continuous function? Well, maybe let me back off. What's the domain of that function? All real numbers. Okay? Is it a continuous function all over that domain? Yes, it's a polynomial function. Polynomial functions are always continuous on the real number line. All real numbers. Okay? Also, it's a smooth function on that whole number line. Never has any points or cusps or breaks or anything else. It's always smooth and continuous. Okay. I think that's all we need to say about that. Here's g of x.
I'd like to actually see that. Would that be just a larger parabola?
It probably is going to have, it's going to be going up in both directions here.
Right.
Okay, because the leading term is even power. So it's going up and its coefficient is positive. Okay, leading coefficient is positive. The odds are it's going to come down, or let's see, start on here. Come down, go up, down, and up.
Okay. So
Now,
that's where the 3 comes in, where it, gotcha.
Yeah. If it didn't have any cross terms in there, like the x cubes and the x's, it could then come down like a parabola, flatten out, be up straight here. Yeah, that would be it if it was 3x to the fourth minus 8, say. That would be like that. Just offset a little bit because of the 8.
Gotcha.
No, offset this way, vertical offset. But this one, no, it's got cubic terms and linear terms, which I call cross terms or something like that, and that's probably going to introduce the, here's how I think about it. Coming down like this, it introduces some wrinkles in here.
Right.
So therefore, something's going up, something's going down, but you'll have no more than 3 changes of direction. It could come down, go up, down, up. No more than 3 changes of direction.
Yeah, well, I was just thinking, too, with the cubed, it's always, function kind of like that. So I was thinking, it's kind of like a parabola, but just with that at the base.
With some wobble in the middle.
Right.
Yeah, okay. Yeah. That's not in the math book. You won't find wobble in the middle. Okay.
Come on now. It's
Okay.
not defined as that. Yeah.
Well, you have to have the visual with it too, wobble in the middle. Okay. All right, here's g of x. X plus 3. Oh, we didn't do the second part. P and x are both polynomials. The P of x is always continuous and smooth on the real number line, everywhere on the real number line. So P of x divided by Q of x is continuous everywhere. Oh, yeah, we did do that. Yeah. Okay, I'm sorry, we did. It just looked smaller, and it was. How about this one? G of x is x plus 3 over x squared minus 1. Okay? Now, when you see g of x, what should be the first thing your eyes focus in on, you focus in on, and you deal with?
Trying to find the values that wouldn't work.
Yes, exactly. And why would you do that?
Because that way you know that you can go and get those out of the way and know that those aren't going to be values that you can, because they're going to be discontinuity or
right.
Yeah.
And they'll be, well, tell me what they are.
Open circle or
yeah, no. not, actually
Oh,
none of
you're
that
actually,
circles
I
here.
know, so the positive one?
Is, okay, is one place that x cannot be positive 1. Any others? X can't be negative 1 either. Okay, so you got 2 places that x cannot be. X cannot be, picture those as vertical asymptotes. Can't ever be there. Therefore, as the F is approaching either of those vertical asymptotes, either from left or right, it's going to some infinity. Maybe same infinity, different infinities, I don't know. But guess what? Those are infinite discontinuities, x equals plus and minus 1. Guaranteed. Okay? Now, not jump discontinuities, not removable discontinuities, and not undefined or something like that. They are infinite discontinuities. Okay? So it will be continuous anything left of minus 1, in between minus 1 and plus 1, and right of plus 1, but not even defined at those discontinuities. So those are infinite discontinuities. I think that's all they're looking for here. Okay? It's continuous everywhere except where x equals plus or minus 1. All right. Now, I knew there was something else I want to say with the first. What makes this a polynomial? The f of x a polynomial. What is required for that to be a polynomial?
To have more than 2 terms? Or a binomial, so...
Okay, actually, f of x equals 3x to the 4th would be that's a 1-term polynomial.
Okay.
The poly doesn't mean very many, okay, but it has that. So it's not the number of terms
Is it the powers
necessarily.
then?
What about the powers?
It has to be, the number of powers has to add up to more, or, no? That's going to be positive.
The exponents always have to be positive, okay? Or at least non-negative, okay? What's the exponent of this one? X. 1. Okay. If you had a plus 7 out there, that would have an exponent of 0. That's still not negative. But not only that, they have to be positive exponents. They also have to be, because see, a negative exponent would put something in the denominator. If that was x to the minus 1, that'd be 8 over x. As soon as you put that variable in the denominator, then you're going to have places that could be 0. You'll be in this situation. Okay, so you have to have positive exponents, not just positive or non-negative exponents. They have to be whole number exponents. This could not be x to the 1/2. Right? Because x to the 1/2, what's another way to describe that?
It would be 1 over something, or excuse me.
X to the minus 2 would be 1 over x squared.
Right.
What is x to the 1/2? What's that again? Now, x to the negative 1 is 1 over x. That would have it in the denominator. What's x to the 1/2 represent? Second? Square root. Very good. The denominator of a fractional exponent is the index of a fraction. So x to the 1/2 would be square root, x to the 1/3 would be a cube root, x to the 1.5 that would be 1.5, then it would be a square root of x cubed. That's what. Can't have that and be a polynomial function, because polynomial function is defined everywhere. A square root function only can have positive value or non-negative values as the square root. So yeah. So not only be a polynomial, positive integral or non-negative integral exponent. Coefficient can be anything. Rational, irrational, positive, negative. Yeah, it doesn't matter. Pi, e to the 7th, whatever you wanted that to be. Okay. But would sine function be a polynomial function? Smooth and continuous. Sine function. Sine function is not a polynomial function. Okay. So, I think we beat that to death, didn't we? Okay, let's see. Where are we? Okay, that's theorem 2. Let's go to theorem 3. Ha! This is sort of getting to some of the same stuff I was just talking about. Continuity of some basic functions. What would you define this function to be? Just what I was saying. This would be, I don't know if it has a special name, a radical. This has a root symbol in it, okay? It's the n would be the index of that root. Okay. You need my key, or you need to get in next door? I'll just my key. Okay. You know which one, or you can try it too. Okay. All right. So that is a radical, what I call a radical function. It's continuous on its domain where n is a natural number. What's another word for natural number? Second? Not real. Real would include decimals, fractions. A natural number are your counting number. It's almost whole number.
Okay.
The what difference between a natural number and a whole number is just one little difference, and it's not much of a difference.
It's zero.
Zero. Zero is a whole number. It's not a natural number. Natural numbers are 1, 2, 3, 4, 5, 6, 7. The counting numbers. So if n is a counting number, you see, n can't be zero, can it?
Exactly.
You can't take that would be a undefined exponent, and we don't usually take those. Okay, so it has to be positive accounting number, a natural number. You could call it positive integers. That's what I'm starting to say, but that's simple. Just call it natural number. Okay. It's continuous everywhere on its domain, and its domain would be, here's the problem here, folks. For n a natural number, if that n is an even number, the domain is only values greater than or equal to 0. If n is an odd number, domain is all real numbers. Okay? So, but that cheats its way around to say on its domain. Everywhere that's defined is continuous. Okay? What's that? Okay. If this n were even, then that would be like a square root, or a fourth root, or a sixth root, or an 82nd root. You know, any even number there. And remember, they have to be natural numbers, counting numbers. Because you can't take the square root of a negative number. You can't take the fourth root of a negative number. You can't take the 10th root of a negative number. You can't take an even root of a negative number. So that, its domain would then be everything greater than or equal to 0. Okay? The x, domain of the x. But if n is odd, it could be any number, or positive or negative. Doesn't matter. That would be all real numbers. But that's why they weasel the way around it to say anywhere on its domain. If it's the even number, it has to be non-negative domain. If it's an odd number, any domain. Okay, sine and cosine, the trig functions, they're continuous everywhere, all real numbers, positive, negative, fraction, decimal, rational, irrational, doesn't matter, they're always continuous. Okay? Your power function, no, this is, sorry, I said it wrong. Your exponential functions, y is equal to b to the x. Okay? Now here's the deal. The b is the only thing that's restricted here. We don't let b be 0, so it has to be greater than 0. If we don't let b be negative, it has to be a positive number b greater than 0, not counting 0, but it also can't be 1. Okay, so it can be any number between 0 and 1, but neither 0 nor 1, or any number greater than 1. As long as b is one of those, it can be anything. Continuous for all real values x. Everywhere. Now, the inverse function for an exponential function is a log function. And it's the log of that same base. If this base was b, the log of base b of x. That's continuous, but now it's not everywhere on x. X has to be greater than 0. B, of course, still has to be greater than 0. B can't be equal to 1. So it's going to be between 0 and 1 or greater than 1. That still holds from here, but now your x isn't everything on the real number line, only the positive values. You cannot take the log of 0. You cannot take the log of a negative number. Anytime. Ever. Okay. Just like you can't take the square root of a negative number. You can take the square root of 0, but you can't take the square root of, you can't take the log of 0. Make sense? Okay. Those are just some of your basic functions. Now, what trig functions do they leave out? Tangent, cotangent, secant, and cosecant. Those are not continuous functions on the real number line. They're continuous functions in their domains because they have values where they're not defined. Sine is not defined. No, sine is defined everywhere. Cosine is defined everywhere. Tangent, is not defined where cosine is 0, and where is cosine 0? Your half pi's. Any of your n over pi. How do you say that? 2n plus 1 over pi over 2 pi. That's it. Any of the half pi's. Okay. Cotangent and cosecant are not defined at n equal pi's. Any n pi, or n is a counting number. No, actually, n is any integer in that case. Okay. They didn't go into that. We won't either. Here are some examples. Okay. First one of those, the square root function. This is how it looks. Notice it's defined for x equals 0 and any value x greater than 0, but never for any negatives. Now that could be any even integer there, be the same thing. The shape will be a little different. If that was a 4 there, it comes up a bit steeper here and flattens out through there. Okay? 6 would just be steeper here and flattening out more back there. Okay? And it just keeps on going. So that's your basic square root function. Can't be a negative value. You could put a minus in front of this, minus x to the 1/2. That would bring it down here. But just this function would be only x is greater than or equal to 0, and the y's are always positive. Now, if you're doing a cubic function, cube root function, this is how it looks. Good for all real numbers. Okay. The sine function now, I don't like this drawing for a little reason. Okay. I can't draw on it, but let's go on and cover the rest of it, and then we'll see. This is your basic sine function. I'll work on that in a minute. There is your basic power function, or exponential function. In this form, 0, 1 is always the case. When x equals 0 and y is always 1. Okay? And here, since your base is positive, which it has to be, it can't ever be negative. It's not 1, it's not 0, so we're fine. It's 2. But the x is negative, you're back here. You're doing 1 over 2, 1 over 4, 1 over 16, 1 over whatever. Okay. It's getting closer and closer to 0, but never getting there. And then from here on, it's increasing without bounds. So you're raising to very large powers. Okay. Now, they didn't show the log function. I'll show that in just a minute. But I wanted first to show, whoops, too much. What I don't like about this one, okay? Here, for the square root function, you know it ends right there because it can't be negative, so it ends at 0, goes up like this, and keeps on going. When they don't have anything at the end, it means it keeps on going. This one keeps on going this way, that keeps on going that way. Yeah, fine, I believe it. This one pretty obviously keeps going this way. You see, this also can be negative. That makes it look like x can't be negative. The sign would be negative. It is. So I don't like that representation, and I'm being real picky about it, I think. But this, I think, that should come down just like it did there to indicate it goes both positive and negative. Okay. And then that's your exponential function. Now, they didn't show a log function curve, but the log function curve would look like this. Let me go back to black here, or dark purple, or whatever it is. Here would be how a log function looked. 1, 0 is always going to be on it. It does something like that. Basically, it's the mirror image of this one across the line y is equal to x. That's basically what you get. See, the x value can never be negative. Okay? This is not defined for x equals 0. For x equals any negative value other than 0, you get any value other than 0, you get something on that curve. And I think I already said it's the mirror. So I think that's all we need to do there. Probably more than we should have. Sorry, my throat feels like it's going on me, and it's my fault. I went to a basketball game Saturday night and yelled too much, so sorry about that. Okay. Now, I mentioned the other trig functions. Now they're showing them. The only continuous trig functions are sine and cosine. But here's an example of tangent. Now, what makes tangent not continuous is that what is the ratio identity or the quotient identity for the tangent function? Does anyone remember? Sine over cosine. And guess what? If sine is divided by cosine, cosine can never be 0. Where is cosine 0? At your half pies. Pi halves, 3 halves pi, 5 halves pi, 7 halves pi, 9 halves pi, or negative pi halves, negative 3 halves pi, negative. Can never be any of those, so you have an infinite discontinuity at those vertical asymptotes where cosine is equal to 0. Other than that, continuous anywhere except for those parts that it's not defined. So it is continuous in its domain. It's just its domain has some discontinuities, infinite discontinuities in it. Make sense? And because of similarities then, secant is 1 over cosine. So you have the same discontinuities. The difference there being, I don't think they showed these. I'll show you just quickly. You should remember this from your trig class, shouldn't you, folks that were in mine? The secant function has these same vertical asymptotes at the half pies. Here's the difference though. Let's just assume that is 1 and this is negative 1. Ooh, that's not very even, is it? Let's call that negative 1. Sorry, here we go again. The secant function has the same infinite discontinuity here, but comes down and kisses at x equals 0, value of 1, and then later we'll do the same thing here. And we'll be doing the same thing over here. I'm not drawing too well, but You get the general idea. It never has a value in between -1 and +1. Sines and cosines stay in between -1 and +1. Secants and cosecants never do. They stay outside that. They are equal at 1 and -1 once a period, but they're never outside. They're never inside -1 to 1. Ever. Sorry. My throat's hurting so bad. All right. And they do give a little bit of nomenclature here. Oh, they don't. They should. All right. Let's now look at inverse functions. Do you remember what inverse functions are? This is a sort of silly concept of mine, but they're the undoing functions. They're the functions that undo some other function. Simply, way back in grammar school, I bet you remember, subtraction undoes addition, right? So it's the inverse function of addition. Multiplication undoes division, and vice versa. Addition undoes subtraction. You've always dealt with these without calling them inverse functions, though somewhere along the way you called them the additive inverse or multiplicative inverses. Yeah, you're using the terms okay there. But when you get bigger, hairier looking functions, what do we mean by inverse there? If f of x is continuous on some interval I with a range of r, okay? So it's continuous on some interval I. The interval I is along the x-axis, range of r along the y-axis. Now, if f is continuous on that interval, and if f inverse exists, now there's a big if there. Can anyone tell me where f inverse could not exist? What has to be true about f to make sure it has an inverse? What were you going to say? What's that?
Your domain can be the same.
Okay. Yeah, you flip the domain and range, I think is what you're getting at. But what has to be true about this function f? It has to be continuous, of course, but for it to have an inverse.
Can't be 0.
It what?
Can't be 0.
Oh, it can't. No, this is not 1 over the function. This is inverse function. So don't think of that as like x to the -1. Anytime you have a number written to the -1, that means divided by. This isn't what this means. Good? Yes, though. Okay? F has to be, there's a couple of words for it. The one that, huh?
Smooth and continuous?
It has to be smooth and continuous, for sure. Okay? Actually, it doesn't even have to be smooth. No, it has to be continuous. What F has to be, there's 2 words for it. One, the book uses, and nowadays they use it.
A 1-to-1.
1-to-1 function.
Gotcha.
Okay? Now there's another 2 terms that define what 1-to-1 functions are. The one term is monotonic. Monotonic means it's either always increasing or always decreasing. Okay, that's what it means to be 1-to-1. The other thing that means 1-to-1, the test, to be a function, you have to pass the vertical line test. To be a 1-to-1 function, you have to have pass vertical, but you also have to pass the horizontal line test. Now, any horizontal cannot intersect that function in more than one place for it to be 1-to-1. Just like vertical line test says it can never touch the function more than one place, vertical line. But now the horizontal line test requires that too. So if those conditions are met, f is continuous, of course, on some interval I with a range of r, that gives you the interval. If it's continuous on that interval, and if it exists, meaning it's either strictly increasing in that interval or strictly decreasing 1-to-1 in that interval, f is that would make F inverse exist. Then F inverse is also continuous, but here's the difference. What was the range of R of F becomes the domain of F inverse. And what was the domain of F becomes the range of F inverse. If it's continuous, if the inverse exists. Okay. Now, they do give a couple of sort of like examples here. Oh, not yet. Yes, it does. Okay. Let's talk about what they give you f of x is equal to the inverse sine of x. Okay? Now, let's think backwards a little bit. Let's take the function, this. Okay, let's call it something else. G of x equals sine x. Does anyone know how that graph looks? You better be screaming, yes, of course we do. Okay. How does it look? Okay. Gather from what your arm waving was, it's something like this.
Between one and negative 1, and it goes through.
It's a periodic function, repeats and repeats and repeats and repeats. Now, same amount above and below, my lines aren't very good, but that's how it looks. Is that a one-to-one function? Horizontal line is going to really screw up everywhere. It's either going to have no points on it or an infinite number of points on it. Not good. So therefore, sine x on that domain does not have an inverse. But can you limit a domain where sine x does have an inverse? Okay, from where to where? Okay, negative pi halves to pi halves. That's where it goes from -1 to 1 and doesn't back up on itself. So there is where, on that domain, g of x does have an inverse, and that inverse could be the self of x. So what is that going to look like? Well, you got to sort of think backwards here. Okay? Now your range is going from minus pi halves to pi halves, whereas your range here was, as you said, from -1 to 1, right? Well, that means your domain here is -1 to 1, right? You have to flip the range with the domain. Now, let's take a look at how this looks here. Here, I think in terms of these things, and later when you do calculus, you'll think in terms of them too. Here you have a slope of 0, right? Okay. Gradual increasing around here. Here you have a slope of 1. I don't know if you knew that. That is a slope of 1. And there a slope of 0. Well, the inverse of 1 is still 1. Thank you very much. So that slope is going to be the same. But over here at this point, this has to be not a slope of 0, but basically almost an infinite slope. That's what it looks like. You take that section out of there and flip it. Flip it across the. I don't have to do this, but I think it. Let me see if I can get this right. There's your identity function. And there's your identity function, So basically, those really aren't helpful at all. But you see where this is, and I don't have my points very well find my scaling is way off there. It's a little bit better here, but way off there. In fact, this is terrible here, because this is about a little more than 1.5. That's 1 there. This is a little shorter than that. So my scaling is terrible up there, so that's why the identity function looks terrible. You know, but here it's a little bit better, but still not good. Okay. But anyway, those are reflected across the identity function. Okay. So that was theorem 4. Let's move on to theorem 5. Well, let's see, was there anything? Oh, yeah. Okay, let's go back and do cosine. Do the same type thing with cosine. What does it, go back to black, or dark purple, okay, or deep purple if you like the singing group. Okay. Now, how does cosine function look?
It starts down.
Okay.
It starts up and then
Right, okay, it starts at 0, 1, okay, and then it does this nature of thing. Just like the sine, by the way, repeating and everything else. On what interval, is that a 1-to-1 function? No. How can you make it a 1-to-1 function?
you have to go
Okay. Okay, when you say from and to, be sure you're referring to the x's. From x equals 0 to, where would that be? This is pi halves, 0 to pi. And so you're 0 to pi here. That defines one cycle, no, half a cycle, where it's a 1-to-1 function. Okay? So, how would the inverse cosine looks? Well, whereas here the range is still minus 1 to 1, and the domain is 0 to pi, here you're going to have your domain minus 1 to 1, and your range of 0 to pi. Pi would be somewhere up here, okay? Now, this always drives me nuts doing this, okay? All right. Let's take the point 0, 1, and that'll be corresponding to 1, 0. Remember, inverse function flips those. And when you do pi halves 0, that means 0 pi halves. Right here. Okay? And then do pi negative 1. So that would be negative 1 pi. So if that's pi here, then what you have, and here at the endpoint you have close to, it's something like that, okay? You can imagine this part here flipped across the identity function axis, and that through that part up here, okay? So here's your identity function, we put that up here. So this is how it works out. These aren't meeting here, sorry, let me go and get rid of this one. We're through with that, okay. That's what the cosine function, inverse cosine function looks like. Now, here's something else to notice about inverse functions. If this one's increasing, this one's increasing. If this is decreasing, this is decreasing. They're always monotonic and in the same direction. You can't tell me we're out of time already. Yeah. Okay. We'll start next time at inverse tangent. Sorry I'm taking too long on this. But you will be seeing these things, and you really do need to have kind of a mental image of what they look like. So let's see, have we done enough to have any homework exercises here? We sure hope so, don't we? Your ass we do, okay? I think you can do number 1, number 3. We've already done some of these, like 1 we did. 5. Then do any of the odds 7 through 15. Then do any of the odds 17 through 33. I think you can do any of the odds 35 to 47. Oh, wait. Let's not. Let's leave it to 35 to 43, because we haven't done composites. We'll do those next, okay? And we'll pick up the rest of those next time. Good deal. This is one class. I don't see any of the rest of you later in the day, do I? In my linear algebra class, I see all 4 of those guys later for either Cal 3 or differential equations. So therefore, most of my differential equation Cal 3 students are somewhere else too. So, but y'all are, this is the only time I see y'all. So I'll see y'all Wednesday. Good deal.